Let's talk about another important concept in physics or in mechanics, which is called the center of mass or center of gravity. So we have been learning that if there is no external force, then the net momentum of the system remains conserved. So starting from Newton's equations, we said the rate of change of momentum is the force applied. That's what Newton's law says. Now this is for one body, and this can be actually generalized. The sum of all the forces on all the masses can be written like this. So if you have one body, you have another body, a third body, and there are forces which are acting on all these bodies, then sum of all the forces is this, and because of these forces, these guys will have different momentas. So this is P1, this is P2, and this is P3, and so on. So sum of all these momenta is on the right hand side, and the rate of change of all this sum of momenta is equal to the sum of all the forces which are being applied to all these masses. Well, you see, you can in fact write it individually. Let's say if you talk about just this mass, then you can write sum of all the forces on first particle equals dp1 over dt, and sum of all the forces on the second particle equals dp2 over dt, and so on. But if you add all these equations, this is what you get, right? So these equations can be added on the left hand side and on the right hand side. Okay, but and why we do this has a reason. There's a significance behind doing this, behind writing all these individual equations in one combined equation. So let's talk about that. Okay, but let's first of all talk about this. So let's call this whole P1 plus P2 plus P3 and so on. You know, this is a vector addition, so this should equal to, let's say, a bigger vector P. I mean a different vector P. So this is nothing but a vector sum of all the momentas, right? And in principle we can write this as MV, whereby MV means M is the total mass of the system, which means sum of all the masses, M1, M2 and M3. So M is actually M1 plus M2 plus M3 and so on. And V is the velocity, some velocity, we do not know which velocity, but P can be written like this. So let's see, what is this? P1 plus P2 plus P3 and so on can actually be written as M1 dV1 over dt plus M2 dV2 over dt and so on, right? Oh, I'm sorry, this should be actually M1 dx1. Well, just to make it even more clear, it's actually M1 V1 plus M2 V2 plus M3 V3, where V1 we know is M1 dx1 over dt plus M2 dx2 over dt plus so on. Okay, and this whole thing can actually be written as d over dt, because it's a linear operator. Dt, it acts on the summation, as M1 x1 plus M2 x2 plus M3 x3, right? You see, when it acts on all these particles, it does not touch m1 but acts on x1 because m1 is just a number. So when you open the bracket, you get m1 dx1 over dt plus m2 dx2 over dt and so on. So this is what you receive. Okay, so this is what is equal to, just to remind, the capital P. Okay, and we already have sort of given a definition that we can also write capital P as mv. So we can say m, so we're sort of aggregating over all the particles, equals d over dt over m1 x1 plus m2. This should be actually a vector sign, because you see, you should not forget that velocity is a vector. Even here should be a vector sign, plus m3 x3 and so on. Okay, and that gives us v equals d over dt of m1 x1 plus m2 x2 plus so on, divided by capital M, which is nothing but m1 plus m2 plus m3 and so on. And this whole thing actually is defined as dr over dt, where by this we mean the r, and r is actually called the, this is what it is called, the center of gravity or center of mass of the system. So what this exercise tells is that rate of change of momenta equals to the force applied, which means, in other words, you can say the rate of change of momenta, which is nothing but the momentum of the center of mass of the particle. So you see, this is the momentum of the whole system, and the momentum of the whole system is nothing but rate of and the rate of change of this whole momenta is nothing but the force applied. So you can also write this as F over all the particles is m dv over dt. Does it make sense? So we have compacted this equation in this form. Okay, why is it called gravity, center of gravity? Also, well, we understood this is sort of center of mass. Why it's called center of gravity? Let's say if you have many masses, and all of them are being acted by gravity downwards, then all these forces can be are acting individually, but all these forces can, in a combined way, be written as, so if this is m1, m2, m3, m4, the net force is, I'm sorry, I'm running out of space. The net force is m1g plus m2g plus m3g plus m4g, and this is in the downward direction. This is same as writing, and you see these are different vectors acting differently, and this is same as writing mg, where m by mg we mean this is the center of mass. Let's say this is the center of mass and this is the total mass. So this left hand side is nothing but a vector sum of all the gravitational forces acting individually on the particle, is same as mg, where m is the total mass of the particle and g is the gravitational field. So in a way you can say that this system which I just redrew it, is equivalent to this system. And this is all because the way we defined this, constructed this. So this system is equivalent to that system, right? This is the moral of the story. It will become more clear when we will discuss some examples on this.